Welcome to the final part of Lecture 7 on this course on Computational Fluid Dynamics. In this final part of Lecture 7, we're going to go through one of the key algorithms that's used to solve the discrete form of the Navier Stokes Equations, the Semi-Implicit Pressure Linked Equations algorithm, or SIMPLE. We'll see that the SIMPLE algorithm isn't actually that simple, but it is elegant and very, very effective. Before we go through the steps that the algorithm takes, we're going to examine how the pressure field is linked to the velocity field. What we'll discover is that a very, very approximate form of the Navier Stokes equations is used as the pressure correction equation, which is the name of the equation that links these two fields together. The SIMPLE algorithm starts by using the discrete form of the x and y direction of the Navier Stokes equations that we derived in the last part of this lecture to improve some sort of initial guess of a velocity field. The neat trick that then gets played is not to solve the continuity equation directly, but rather to assume that it has to apply and just invoke it. When done in the right way, specifically in conjunction with the pressure correction equation, it allows the initial guess of the pressure field to be improved. The SIMPLE algorithm is an iterative algorithm, and so the sequential improvement of the pressure and velocity fields should eventually lead to an answer that's fit for purpose. So the first thing we're going to do is look at this pressure correction procedure. Now, what this relies on is an initial guess of not only pressure, but also of the different components of our velocity field, our x direction and y direction, if we're dealing with 2D Cartesian coordinates. And so every guessed parameter here I'm going to put an asterisk by. So P star, U star and V star are the guessed pressure, x direction and y direction velocity fields respectively. Now we need to define what we mean by a guess, an error and a real parameter. So let's say what we're trying to achieve is the calculation of pressure. There we go, there's pressure, that's what I want to calculate, and I'm going to call that my real pressure. That's the parameter that's actually of interest. My real pressure is going to be equal to my guessed pressure, which in this case is a designated P star, but also some sort of error that I don't know. And so any dashed quantity is going to be an undefined error. And so in this case, P equals P star plus P dashed. Now, I'm going to call this equation D. We'll come back to this later on. We can apply the same logic, of course, to any of the fields that we're solving for. So my x direction velocity u and my y direction velocity v will also be equal to their respective guesses, u star and v star, plus their respective unknown errors, u dashed and v dashed. Now, when we are making a guess and solving the Navier Stokes equations, we already know what u star and v star is. Either at the start of the solution process, they're the guesses of the fields that have been made, so if you like, they're kind of an initial condition. And as the algorithm progresses, u star and v star are just the values of the velocity in the x and y directions at the previous time step. And so what we can do is to try and work out how we relate u star to u dashed, v star to v dashed, and importantly p star to p dashed. And we'll develop a formulation for this over the coming slides. Now, what we're going to focus on is an equation that allows us to calculate P dash, the pressure error. The pressure error, as we'll see in a minute, is our key means of linking the pressure and the velocity fields together. And so, if we're going to do this, we need a suitable equation to do that. Now, we could say, right, we know exactly how pressure is linked to velocity, because it's linked via the Navier Stokes equations. Here is my x direction, and there is my y direction Navier Stokes equations written out in full, but with each term now posed as an error term. And so one could argue that, well, I can evaluate P dashed if I know the errors of everything else, u dashed and v dashed. However, this is cumbersome. We're already solving the Navier Stokes equations in another form at a different step in the algorithm. What we're looking for is an approximation to evaluate P dashed. Don't forget, we've got an iterative algorithm, and so if our approximation is poor, it just means we need more iterations to solve the problem. If our approximation is reasonably okay, then it'll need fewer iterations to solve the problem. So we're going to make a bit of a sweeping statement. We're going to say, let's arbitrarily ignore the complications here. All I want to do is figure out what my pressure error is in terms of my velocity errors. And as we'll see in a minute, that gives us a cunning way of working out continuity. So I'm going to ignore the second and third terms on the right hand side in both the x and y direction Navier Stokes equations when they're rewritten in terms of an error. And I'm just going to say that du dash by dt is going to be minus 1 upon rho dp dash by dx, and similarly for dv dash by dt. Bit radical, but what we can then do is figure out what that looks like in discrete form. So if we look at the x direction Navier Stokes equations, u dashed, we've already said that, well, u dashed of t plus delta t is going to be whatever the error u dashed was at a previous time step, plus now how I change that estimate, and that's going to be my 1 upon rho plus my pressure spatial derivative, and I've used a centered difference here for my pressure node. So I can relate my velocity error to its previous velocity error, which I don't know because we're not explicitly calculating errors, to my pressure error. Well, this seems a little bit strange, so let's make another simplification. All I care about is an estimate of pressure error in terms of velocity error, and we'll see why it's important that we know pressure error in terms of velocity error in a minute. So this has to be done at the same time step. I'm interested in calculating the pressure error at time step t plus delta t. I don't have velocity error data at time step t, so I'm simply going to ignore it. And so what I end up with is an approximation, a very rough approximation, that allows me to link pressure error at time step t plus delta t to velocity error at time step t plus delta t. Now, let's call these equations here E and F, E for U dashed and F for V dashed. Now what we're going to do is we're going to see how all this ties together, because at the moment it still seems a little bit arbitrary. Now, what we have is continuity. Remember, what we said is we're not solving for continuity, we are invoking continuity. We are saying that continuity is true. If we're going to invoke continuity, we need an expression for U and an expression for V. We know that we can write U and V in terms of U star and U dashed and V star and V dashed. However, what we've just done on the previous slide is relate U dashed and V dashed to pressure. We linked together U dashed at t plus delta t to terms involving P dashed, which is F of P dashed in this board, or terms at V dashed of t plus delta t in terms of P dashed at t plus delta t, which was G of P dashed. So if I substitute in F of P dashed for U dashed and G of P dashed for V dashed, what we have are two equations for my x direction velocity U, my y direction velocity V, that just involve my guessed velocity field and my pressure error. Okay, so in effect what I can do is say that d by dx of U star plus F of P dashed plus d by dy of V star plus G of P dashed, which is du by dx plus dv by dy, equals 0. Now let's think about this a little bit carefully, because this is a key step. We have got U star as a known quantity. We've got V star as a known quantity. What we'd like to do is to calculate P dashed, which is unknown, from those known quantities via the application of continuity, which is what I've written on the board here. Okay, so let's think how we can break this down. If we look at the x direction velocity, x direction, and let's say we discretize this spatially, we can see that U star we can write as a centered difference using that halfway node in the x direction. So at I plus a half comma j, we can say that du star by dx is going to be U star at I plus 1 comma j minus U star at I comma j over delta x. We know how to do that. If we look at d by dx of f of p dashed, it's a little bit more involved, but we can discretize the derivative of f of p dashed in the x direction as well. And so what we'll end up with from those terms in red is a U star at I plus 1 comma j, a u star at I comma j, and then functions involving p dashed at I plus 1 comma j, p dashed at I comma j, and so on and so forth. We can of course do the same for the blue terms. And so v star is going to be discretized spatially in the y direction, so dv star by dy. We know we can discretize at our halfway y direction points, and so as an approximation, dv star by dy we might take as my v star at I comma j plus a half minus v star at I comma j minus a half over delta y, which will give us v star terms, and then we can do the same when we discretized g of p dashed. It'll be a little bit more involved because it's a second derivative, but we will get some terms involving p dashed at nodal spacings. Okay, so we can effectively write a discrete version of continuity if we were so minded. Now, what we're going to do is we're going to put all the velocity data together in one place. So rather than having a vector of velocity u star and a vector of velocity v star, imagine these as column vectors if you will, what I'm going to do is put my column vector u star on top of column vector v star and call this big U star. Okay, and so for my spatial derivatives I know that I've got a u star at I plus 1 comma j, I minus 1 comma j, and a v star at ij plus 1, ij minus 1, and so on and so forth. But all that data of velocity can be held in one vector rather than having to deal with two vectors. We just stack them one on top of each other. And if we look at what pre-multiplies u star and v star at the various nodal positions, we'll have various things involving delta x and delta y, all of which we can put into a matrix M1. So M1 u star is effectively the parts of the continuity equation using the guessed x direction and guessed y direction velocity suitably discretized, and of course we know that information because we know u star and v star. If we turn our attention to p dashed, when we take the second derivative effectively of p dashed, because we've got d by dx of f of p dashed, and f of p dashed is already a derivative, and likewise d by dy of g of p dashed, with g of p dashed also being a derivative, we've got second derivative terms for p dashed. And remember, we don't know p dashed, but nonetheless we can write p dashed as a column vector, and we can pre-multiply that by a matrix which gives us all the various terms that allow us to write the discrete form of the continuity equation correctly. And so we've effectively got M2 p dashed as being the matrix vector equation that describes that. And so what we can write from our continuity equation is we've got this matrix M1 times this overall velocity vector big U star, which we know, plus M2 times this velocity times this pressure vector p dash, which we don't know. But what we want to do is to calculate p dashed. So having decomposed it into matrix vector form, hopefully we can see that what we can do is we can write p dashed as a matrix inversion step. So p dashed is simply minus m1 u star all multiplied by m2 inverse. I've written that as equation G. And so calculating my pressure error can be done by using this matrix inversion from known values of guessed velocity field. So this is the key matrix inversion step within the simple algorithm, and typically for an arbitrary engineering geometry you would be using an indirect method for this. Fluent would be using AMG, ComSol Multiphysics would be using GMRes. So now that we've introduced those steps of pressure correction, let's see how the algorithm hangs together. So the simple algorithm starts with a guess. It guesses the pressure and the velocity fields. So U star, V star and P star are all known at time t. Okay? Again, when you initialize a Fluent solution, you will see that it goes through some steps, and what it's doing is it's calculating U star, V star and P star. The next thing that then happens is you say, right, I know everything at time t. Time t could be time 0 if you're just starting the problem. And what I want to do is to update those guesses. So I need to know what the values of my fields are at t plus delta t. And so we'd use equations A and B, and remember equation A and equation B was derived in the last part of this lecture, and they were how you update in time your x direction and y direction velocities. And I've put there on the board a reminder of what we derived last lecture. Remember that u of t plus delta t is equal to u of t plus shadow a delta t, and likewise v of t plus delta t is v of t plus shadow b times delta t. So there we have on the board what shadow A and shadow B are, and of course those are the full terms of the Navier Stokes equations, suitably discretized on a staggered grid with a stencil that I've shown above. So knowing U star, V star and P star at time t, which might be time 0 because it might be the first time step, we can then update using equation A and equation B what U star and V star are at time t plus delta t. Okay. So we've got updated velocity guess information. Now the next thing we need to do is to figure out what the pressure error is, because we can then use that pressure error in a subsequent step to update the pressure field guess. So what we need to do is this matrix inversion step to guess our pressure error. Now it needs information pertaining to my velocity fields, which I already have. I've got U star, because remember big U star was a concatenated column vector consisting of the x direction velocity vector above the y direction velocity vector, and these two matrices are just these matrices of terms that we're used to seeing by now that allow the vector matrix equation to be written out. And so that's a reminder of equation G, which allows us to calculate the pressure error. And I'm taking values of velocity information at t plus delta t now, so I can calculate the pressure error at t plus delta t. The next thing to do is, knowing the pressure error, I can update the pressure, because quite simply we said that my pressure by definition is my guess value plus the error. P star, my guessed value here, I know already. P dashed I have just calculated with that matrix inversion step, and so equation D allows me to update at time t equals t plus delta t what my pressure field is P. So by the time I've got to step 4 in this algorithm, I now have updated velocity field information, U star and V star, and updated pressure information, all at time step t plus delta t. So the next thing to do is to see the difference between the pressure at the previous time step, t, and the current time step, t plus delta t. The question we then ask is the error in pressure between these two time steps significant? Is it above or below our convergence criteria? If it's above our convergence criteria, we say, right, we're not converged. We're going to set my new pressure guess at time t plus delta t to my actual real pressure at t plus delta t. And then we're going to start the algorithm again. And we're going to work now out, using my updated guess of pressure field, what my updated guesses of velocity field have to be at t plus 2 delta t. And we'll go around this little figure of 8 loop until we have an acceptably small difference between the pressure fields at the current time step and the previous time step. So when that happens, we say that convergence has been reached and we display the result. So that is the algorithm that is the semi-implicit pressure linked equation algorithms, and this is one of the core algorithms that is used to solve the Navier Stokes equations numerically. It's very, very commonly implemented in CFD software. It dates back to a publication from Patanka and Spaulding in 1972, and I've put the reference there on the whiteboard for you to have a look at if you're interested. And this simple algorithm is the default solver within Fluent. So whenever you hit solve, if you haven't changed any options, this is the algorithm that will be solving your problem. Now, of course, the simple algorithm is by no means the only algorithm. A lot of time has passed since 1972 and other algorithms have been developed. Algorithms have been developed that have been revisions and extensions of the simple algorithm. So you might come across SIMPLEC, simple revised, it dates from 1979, and might achieve a slightly quicker rate of convergence compared to simple, depending on the problem. You may also come across Simple C, which is called Simple Consistent. It dates from 1984, and again is slightly quicker still at converging than both Simple and simple R. It is one of the alternative solvers that you'll find implemented within Fluent. You may also come across a solver called PISO, Pressure Implicit with Splitting of Operators, dates from 1986. Now PISO is designed to be non-iterative. They're designed for time-evolving Navier Stokes equations, and it can be faster than the simple algorithm in these problems. It's another alternative solver that you can find within Fluent. So if you're interested in a comparison of these solvers for different types of problem, there's a very nice review here that was done quite a long time ago now, in 1986, that gives you an indication of performance for PISO, for simple C and for simple R, depending on the type of problem that you're solving. So you've got some choice of algorithms. Let me offer a little bit of guidance. The solution algorithm of choice is problem dependent, and it's governed by stability and convergence rate. My first bit of advice would be use simple to start with. If simple works, fine, it's not a problem. If you're dealing with momentum equations alone, it might be sometimes advisable to try PISO. It might be more robust than simple or simple R. It might converge faster. On the other hand, it just might not. I wouldn't recommend using PISO as the first solver you try. Use simple as the first algorithm that you try, and then if simple works effectively, that's fine. If it's taking an age, maybe try swapping to PISO and see if it makes any difference. If you're coupling momentum transport to another transport equation, for example energy transport or mass transport, try not to use PISO. It's less robust and only tends to work for small time steps. Simple, again, is a very good default solver to use, with maybe slightly quicker convergence with simple R or simple C. It's not particularly clear whether simple, simple C or simple R are superior compared to one another. It depends on the problem. So the take-home message really is to try simple as your first algorithm of choice, and if it works, smile and be happy. So finally, what I'd like to show on the board is how you select the algorithm of choice within Fluent. I've put a screenshot of the Fluent solution controls or solution methods page up, and in solution methods you'll see that there is a drop-down menu that allows you to choose your pressure velocity coupling algorithm. And you'll see that simple is marked there, and that's your default. You've got simple C, you've got PISO, and you've got a further algorithm which is just a coupled algorithm. So some key points to sum up. The simple algorithm was the first and still one of the most commonest ways to solve the Navier Stokes equations numerically. The idea behind simple is that it invokes continuity coupled with a pressure correction equation and uses this result to couple the pressure and velocity fields together in the algorithm. And don't forget, it's the coupling of these two fields that's the key problem that we're trying to work around. There are other algorithms that are based on simple that can sometimes be superior depending on your problem. Simple C and simple R might be the second or third algorithm that you try if simple doesn't work effectively for what you're trying to do. If you're time stepping, the PISO scheme can be used, and maybe if you're solving transient Navier Stokes equations problems, use PISO. So, use simple first, only change the algorithm if you're getting convergence difficulty, but don't forget, don't blame convergence difficulty on the algorithm straight away. The first thing that you should always look at with close scrutiny if you're getting convergence problems is the quality of your finite volume or finite element mesh.